Hello friends, hope you are having a fantastic day. So now we are going to do an awesome lead code problem called rotting oranges. We can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward. We are given an m cross n grid where each cell have one of these three values. First value is 0, that represents that there is an empty cell, which means there are no values over here. Second potential value can be 1, which represents that there exists a fresh orange on that particular cell in the m cross n grid. And next value is 2, which represents that there could be a rotten orange or a bad orange placed in that particular cell. Now there comes the interesting part, that with every single minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So after every single minute iteration, we will start finding more and more rotten oranges, and they would keep on growing. Now we need to return the minimum number of minutes that must elapse until no cell has fresh oranges. That is number one thing that we are being asked. If that is the case, we need to return the minimum number of minutes. And if it is impossible to rotten every single oranges, then we need to return -1 as part of the answer. So let's try to understand this awesome lead code problem. Okay, so suppose this is one of the exampled input that we are given. Now notice that the values are 2, 1 and 0 given in different sections of this 3 by 3 cell. Now we know that value number 2 refers to a bad orange, so I have denoted that as like B over here in this grid, and 1 refers as normal orange, so I have just marked O or like 0, that represents a fresh orange. Okay, don't confuse this with like value 0, because value 0 I have left it as empty because there are no oranges or nothing on that particular place. So now let's focus on our input. Now the way we are given this problem, this is a bad orange. Now let's say that this is the current starting position, so at minute number 0, this is currently what is happening right now. But we know that after every single minute, all the oranges that are adjacent in 4 direction to this bad orange will start getting bad. So after 1 minute passes, we are going to have 2 more oranges that have gone bad, and that are these 2 oranges. So we can mark them as bad oranges, and all the other oranges that we have are going to remain as it is. This happens during the first minute. During the second minute, once again more oranges are going to get bad. So since this orange is right adjacent to this one, this will go bad, and this orange will go bad in the next minute. So these 2 oranges will go bad. So if we mark the number of bad oranges, it is going to keep on increasing in this fashion, and now we are only left with 2 fresh oranges. And during the third minute, basically we are also going to have this orange go bad, because notice that this is directly adjacent to this orange. So during the third minute, this orange will also go bad, and all the other oranges we already have, they are bad. And during the fourth minute, basically because in the third minute this orange is fresh, but during the fourth minute this orange will also go bad, and now we don't have any fresh oranges. So we can say that after 4 minutes, basically every single oranges that could go bad, they have all gone bad. So in this case, we need to return 4 as the answer. Now let's say for the same example, we are basically given one more scenario. Let's see that what would happen in this case. Well, we know that during the first minute, the adjacent orange is going to get bad. So now we are going to be left with 2 bad oranges and few other good oranges. During the next iteration, once again the same thing is going to happen, and now in this next iteration, basically this orange is going to go bad. So then we are going to be left with these 3 bad oranges and then these 3 good oranges. During the next minute, once again same thing is going to happen, and basically we are going to be left with this orange as becoming bad orange as well, and all the other oranges would remain good. And during the next iteration, basically this orange will also go bad. But notice one thing, that despite every single orange being bad, we do not have any particular way for this particular orange to go bad, which means no matter how many iterations we take, even if all the oranges went bad, this orange will still remain fresh. So in this case, because we cannot have every single orange becoming rotten, we need to return -1 as the answer. So this is what is being asked us to solve in this problem. Now I know this problem looks really interesting and really important in terms of many different aspects. So first let's try to start breaking the problem down and start understanding different things on what we can do to solve this problem. Let's say that in this problem we are given oranges like this and all the other cells are simply empty. Logically, what is the most simple thing we are going to do? Well, we need this is the initial position, so we are going to have a value called minute, and in this particular minute we are going to mark that all the minutes that has elapsed so far. So during the 0th minute, this is the position. So during the first minute, what is going to happen? We are going to start noticing that this orange will go bad. Okay, then during the second minute, this orange will go bad. During the third minute, this orange, and during the fourth minute, this orange will go bad. So this case, it's going to take 4 minutes for every single orange to get rotten. So the thing is, we can visualize it very quickly and very easily, but how can we implement this programmatically? So that's where few important concepts come into the place that let me start describing. Number one concept is that basically for every single position we will have to understand that what is the rotten or bad orange, and then we will have to start iterating from that particular element. So far we were lucky that the very first element was actually a rotten element, but let's say in the same scenario, instead of this being rotten, what if this was a rotten orange? Once again, the answer would still be 4 minutes, but in this case we would have iterated over all of these cells before finding this rotten cell before we start branching out. So that is number one thing, that we need to first of all find that what is a rotten orange. Okay, that is number one thing. Next thing is, the moment we find the rotten orange, what we do is we start branching out. But the question is, are we branching out in the depth first manner or a breadth first manner? Well, logically in this case we are actually iterating in the breadth first search manner, because for every single node that we iterate over, we try to iterate all of its neighbors before visiting before visiting their neighbors. And let me give you a very simple example for that. Let's say in this example, during the very first iteration we simply visit this neighbor. Okay, so we are going to mark this as a bad orange. But in the next iteration, rather than going in one particular direction, we are going to branching out in two directions and marking both of these as bad apples. And then after exhausting all the neighbors of this particular orange, then only we will start exploring more neighbors of these remaining oranges. So this is also another important point to be understood. Okay, that we will actually have to use breadth first search in this case to solve this problem. Okay, we took care of two items. Now let's try to understand that how we are going to keep track of the number of minutes. Well, logically the answer is quite straightforward, that whenever we have to make any single new BFS call, we are going to keep track or keep incrementing the number of minutes that we will have to make. So this would be our minute counter that we are always going to update with every single new BFS call we make. Now we know that in order to use a breadth first search, we will have to use a queue, and logic is quite straightforward, that first of all we are going to iterate over all the oranges that we are given and try to find all the bad oranges we have. In this case we only have one bad orange, but it could be possible that we may be given multiple bad oranges. So let's say that we are only given just one bad orange, so we are going to put this bad orange in the queue, and with every single iteration we are going to branch out in all four directions from this bad orange. The moment we identified a good orange, we are going to mark that also as a bad orange and push it down the queue in order to be processed in the next iteration, and that next iteration will happen in the during the next minute. So this is the second important logic that we will have to understand, that how we are going to be processing the queue. Now comes the interesting question, that how would we know that we have actually isolated or completed every single oranges that we could, and whether we need to return the minutes or do we need to return -1. So for that, during the first time when we are actually iterating over to find all the bad oranges and pushing them on the queue, at the same time we are also going to have a counter that stores the number of good oranges we have. And what we are going to doing is that, let's say in this case we realize that we have 4 good oranges. Now every single time we add one value to the B, we are going to reduce one element from the good oranges. We are going to be doing the breadth first search as long as that we are able to reach some oranges, and then once we get out of our loop, we will try to check that, hey, uh, do we still have any more good oranges. So in this case, we would not have any good oranges, so we can simply say that we did not find any good oranges, so we can return the minutes. If we do find some good oranges, then we need to return -1. That's it. This is the whole problem and this is the whole solution. Now I know that we can use queue plus we can use recursion to complete the BFS call. Also, for this given m cross n grid, we are actually treating it as an adjacency matrix for our graph kind of problem, and every single node we are treating it, every single node that contains the value of either a bad orange or an orange as a node, and connection or the neighbors of each other are being treated as sort of like edge between them. If we see time and space complexity, in this case, time complexity is going to be simply big O of V multiplied by E, vertices multiplied by edges. And for the space complexity, well, since we are not using much space except storing a queue, the space complexity would be directly dependent on the number of bad oranges or number of total oranges present, because in the worst case, we might have all the oranges that might go rotten. So this is the whole time and space complexity. Now let's quickly see the coding solution. So my solution would make much more sense over there. So the very first thing we are doing is to check that if the given grid is equal to null, we can simply return -1. If that is not the case, we are going to define the values of m and end. Then we are going to initialize a count called fresh count. This is to store the fresh oranges that we have at the beginning of the queue. And then we are going to start our queue where we are going to be storing all the rotten oranges that we found so far. Now, the first thing is count the fresh oranges, and we are also going to push down all the rotten oranges down to this queue. So we simply use two for loops to iterate over all the values, and we are going to be counting that what are all the fresh oranges we found. And if we identified that the value is 2, which means that particular cell position is a position of a rotten orange. Okay, so now that's good. Now the very first thing we are going to check is for the edge case, that if there are no fresh oranges, we can simply return 0, that during the 0th minute all the oranges are rotten. If that is not the case, we are going to initialize a variable called minutes with the starting position 0, and we are going to have direction array to iterate over all 4 neighboring directions for any particular cell. So these are nothing special, just the 0 and 1 combinations of adjacent cells, and that we can simply add to the current I and j positions. Now we start our BFS operation, where we first check that if the given queue, we are going to iterate until the given queue is not empty. First thing we are going to check is the size of the given queue. Then we are going to check that for any particular given I position, while it is less than the size of the queue, we are going to first of all pop one element out, marking it as rotten, and then we are going to be iterating in all 4 directions. So notice that with the by using the direction variable, we are actually going to calculate the x and y positions of all the adjacent cells. Then we check that are we going out of bounds. If we are not going out of bounds, then we are going to be turning the fresh oranges into the rotten, and we are going to be reducing the count of the fresh oranges that we found so far. On top of it, we are also going to be updating the rotten queue and adding those values inside our queue as well. Lastly, we are going to be updating the minute variable for every single new breadth first search operation that we make, because this is the increment timer for every single level of BFS. Now, in the end, we simply have to check that if the given fresh count is equal to 0, we are going to return minutes. If that is not the case, we are going to be returning -1. That's it. Now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast, and it beats 99.99% of every single solution, which is pretty great, pretty awesome. Once again, you can see the coding solution on our GitHub repository, so feel free to go ahead and check it out. Thank you.